Oh, okay. So I don't know. It wasn't linking up, but now it's linking up. All right. Sorry about that. All right. So I was saying, right? So we have this. I created an X matrix. What was the dimension? 150, comma 4, right? And then I created a W matrix. And what was the dimension of that? 4, comma 6. But I also changed it then to 4, comma 3. And both of those have very important meaning. Okay, so let's, this or 4, comma 6. Oh, sorry, 4, comma 3. 4, comma 3. So, so then I did a matrix multiplication. So I did torch dot map mul x w. I'm gonna go with this one first, okay? But then I'm gonna use the 6th one as well. I'm using that one first. So this one produced an H1, which was 150, comma 3, right? That's what the output was that we had. So another way of looking at this operation that I just did is I'm saying to you, this is a neural network. So essentially what I'm saying is this is also, right? So a neural network like this, you're multiplying this times a set of weights here. So it went from being 4 to being 3. But because there's 150 samples, we do a batch of 150, you're doing that for all 150. Do you see that? Pardon? Yeah, so what I'm saying is this just means that we're performing that operation for 150 samples, right? But you can isolate it to just one, and it's essentially a neural network where you take the initial 4, right? That's these 4 values, and given the weights, you convert it into a vector of 3. So for each sample, you go from vector of 4 to vector of 3. 150 times. So I had 150 samples. Do you all agree, right? So like all of you, maybe all of you right here, however many, 20 people, right? And you're holding a tray of 4 glasses. I mean, it's some weird analogy, but each of you is holding a tray of 4 glasses, right? Then I do this operation. And now you're all still here, all 20 of you, but you're holding now a tray of how many glasses? 3. Do you see that? I transformed you, all of you, via a neural network. So this is the neural network as it looks, because when we write the neural networks, we don't put how many samples we have in there. We don't say 150 or 1,000 or anything like that. But what's important is that the underlying operation that's happening, the matrix map mul is X times W. So what is X? X is this one. And W is just the matrix connections. Do you see that? Yeah, go ahead.
So,
No.
so we took 150 samples that only had features.
Yes. Yeah, we did that. You built the architecture. It just the weights are still random because I had random values. That second part is the training. So it's like you build the architecture and then with that architecture you train. But yes, you said it, that's exactly what we're doing. Because when we're done, what happens is you grab sample 2, right? From this list, you send it through here and it's going to convert it into this vector of 3 with values. So let's say that the value is 0.02, 0.01, and 0.97. Which one do you think is the class? 0.97. Do you see that? So there's a difference between building what I call like the machinery, the pipeline, whatever it is, but with random values. And then the training just fills in those random values with actual values, right? So in my operation that I did, it's all random. So essentially, I can take each of those 150 samples, reduce them to this vector, and then I can treat that as the final result. Obviously, in my operation, all of these values are currently random values, whatever they are. So there's no meaning because no learning has taken place, but you created the neural network. You can literally use this network. It's just going to give you random values, but it's a thing that works now. And so it'll just give, oh, I think it's this one or that one or that one. Do you see that? It's all through a matrix multiplication. So the matrix multiplication happens here because you have the number of, you have the X times the W to produce the next layer, which is H1. Whatever that hit. Or in my case here, because I'm implying 3, so I'm actually implying that that's Y, the final output. It's that Y that we talked about last week. Do you guys see how straightforward that is? So that's essentially how it works. Now, let's say that I want to have a hidden layer, like a layer in between this input and this output. Okay, why not? So that's where this one comes in. This one comes in, right? So now let's take a look at this one. So I'm saying X is 150, comma 4, and W, I'm going to do a matrix multiplication, is going to be 4, comma 6, right? So what am I doing here in terms of a neural network? And I want this, now I know this is iris data set, right? So because this is the iris data set, obviously it doesn't have 6 outputs. It has 3. So this has to be some kind of a stepping stone towards the end or a transformation. So I'm transforming, right? So what I'm going to do is 1, 2, 3, 4, because that's the input, right? Times a W, but my W is now 4, 6. So essentially, one, two, three, four, 5, 6. I transformed each sample, analogy of holding glasses. I had 4 glasses, now I have 6 glasses. Do you see that? And then from those 6 glasses, what do? Create another W2 that will do what? Map from 6 to 3. And that's the next hidden layer that gives me the classes if that's what I want. It doesn't matter. It's just doing matrix multiplications. You as the architect decide which one is the last layer and at which point you extract the values. Remember that when something comes out of here, initially it's totally random. But in the learning process, you're going to have, let's call it the real data or the labels, right? So maybe these values are like 0.20, 0.20, 0.20, just random. But this is going to be 0, 1, 0. So the model during training will compare this one to this one, minimize the error, and start the process of improving this prediction here. Eventually, if you've trained correctly, what's going to happen? What I said before, this value now will be 0.01, this one 0.01, and this one is going to be 0.98 in a good model. Do you see? But all the architecture you just did with these matrix multiplications. Yeah, go ahead, please.
Is there any
The middle, so the weight or the result here? There is an intuitive way, actually. So the vector space model. So in the vector space model, so this is a vector space model of R for This is a vector space model of R6. Do you see what I'm saying? So for instance, think of it like, this is well, actually, I can do a better one. Let's do 2 and 3. So R2, like that, right? What is it? A plane. So we know that iris is petal length, petal width, sepal length, sepal width. But we only do petal length, petal width, because it turns out that actually the other ones are not necessary. We have 100. So this is a vector space, right? We talked about this last week, right? Then we have 150 samples of setosa, virginica, versicolor. Turns out setosa is about there, virginica is about there, versicolor is about there. Do you guys see that? So these are the different samples, and we're able to already represent them, right? And this is, so I drew these X's, but remember, these are points, right? So these are just points. So I can, petal length, petal width, right? Here's another point, petal length, petal width, right? And it helps you to classify it. That mapping from 4 to 6 is equivalent to me doing R3. So now, you see that? So why is this useful? So let me tell you why this is useful. So actually, I did this wrong. So I should have done something like this. Initially, the data is written in such a way you see there's zeros and there's stars. And you can't really separate it out originally. But because the neural network is training over data, and remember, it's got these weights, right? What the weights are doing is they're trying to figure out a way to do something like this. By adding another dimension. Do you see that? So in this case, I went from 2, and I couldn't separate the data. I add a third dimension, and then I pull out the circles from the stars. But it's not a human that does it intentionally. You just let the neural network play with the values. So essentially it's like you have to think of it like this. So think of it in iterations, right? So it tries a set of weights. Let's say it tries a set of weights. And that set of weights does so it does that, but the circles are still like there. So it tries another set of weights. And it says, okay, that didn't work. What if I try these other set of weights? And obviously it selects the weights in an intelligent way. And it does that. Okay, this is starting to almost look good, but that didn't work either. I'm going to keep training. Eventually, it finds a set of weights. Oops. That could do what I had drawn initially. And that's exactly what it's looking for, right? So it maps from one smaller space to a bigger space. So in our example, we went from R4 to R6. Obviously, I can't draw that, but the analogy is essentially the same. Yeah, please.
It's like trying to explain to a kid, like, pick a preference for the car.
Mhm.
You tell them one has four-wheel drive and a number of doors.
Mm-hmm.
And then the kid looks at it, and that doesn't help them decide if it's a truck or a car.
Yeah.
But they also realize this other variable you weren't considering, like, this one's louder than the other. It's like outside of
A new variable, yeah. So well, yeah, actually, except that here, to go with your flow of reasoning, here I knew pedal length, pedal width. Here, I'm just going to call this latent 1, latent 2, latent 3. I don't actually know what these mean.
Yeah.
Only the neural network knows what they mean because it was able to find this space where at the end of the day, what matters is the model is going to predict with a certain performance, right? And you want that to be the highest possible. So how it did it, you don't quite know. It might turn out that if you start to analyze very deeply, going with your analogy, yeah, it was the horn. This was actually a horn that was somehow being captured. But that the neural network doesn't do because it's all statistical, right? Yeah. The weights are being calculated by the neural network, yes. So the set of weights that, you take this, you specify that this is going to be R3. You do specify that. But it figures out where it puts these values by changing the weight values. Does this make sense, guys? Yeah. Yeah. So this is, yeah. So that's why I said the vector space model is such a profound thing because it allows, this is how you represent the data. And that's essentially what's happening here. So the matrix multiplication is, again, transformers. You're transforming the data, right? And there's a few other things that you do, but essentially the key operation is the matrix multiplication. All right. And so when I take 150 comma 4 and I apply this weight matrix, it gives me 150 comma 6. So you can think of it as every single sample is still represented there, but now it's not a vector of 4, it's a vector of 6. Petal length, sepal length, all those don't really exist anymore. The 6 new exist, and they have meaning only to the neural network for the specific tasks that is doing of classifying between versicolor, Virginica, and Setosa. If you wanted to classify like which one is older and younger, it doesn't work for that. It only works for the specific task. Yeah.
If you want to get it back to 3, then your W sub 2 will be 6 comma 4. Or 6 comma 3.
6 comma 3. Yes, exactly. So that's so that was the last part, right? So now we can perform another matrix multiplication because why not, right? So we can do that. Exactly. So now we're going to do, this is 150 comma 6. So we need now W2. So this is W1. So this needs to be 6 comma 3. Yes, exactly. We need to learn that set of weights. And then once we learn that set of weights, perform that matrix multiplication, boom, we get 150 comma 3. And that's what's, there's training and testing. So during training, 150 comma 3 is compared to 150 comma 3 values here, the real ones. Minimize the error, backpropagate, update the weights, right? That's training. Once you're done with training, hopefully you have a good set of weights. So what do you do then? Now I have a new set of test samples, right? It's going to be, let's say I have 20 of them. 20 comma 4, they go in here, they become what? 20 comma 6, and then they become here 20 comma 3. But guess what? We now know for each one of these 20 what class they belong to, Setosa, Virginica, or versicolor. Do you guys see that? So there's a difference between building the pipeline going forward, and then we got to train. So there's like two mechanisms. Stochastic gradient descent for the training, and this is just right now building the architecture, which is, understanding LLMs and understanding stable diffusion requires mostly this, as the underlying training is just still stochastic gradient descent. Got it? Any questions before we go back to the code? All right, yeah, so that's the intuition, but like I said, a pretty fundamental concept in deep learning. And then other things will happen, like this all these values in each vector go through functions. that will convert whatever values in there to a range of 0 to 1 or -1 to 1, you know, things like that. But essentially the architecture stays the same. Okay. All right. So let me then switch over. So we did that.